side. So we can just write down, here it is. Here's your starting group G, right? Big G here. Slash, and the kernel, what do we say the kernel was? The kernel is NZ. Okay, so you write down the kernel here. K is isomorphic to the image of F. And what's that? Well, it's Zn. Okay, so there it is. So we now know we have this relationship between your starting group Z, the kernel, which is here NZ, and we know that's from the first isomorphism theorem. We know that that's isomorphic to the image of F, which is this. Okay? So we have this relationship, which could be interesting. That's the sort of thing you can use elsewhere, for example. It's an interesting relation. All right, second example. So that was mapping integers to residue classes. This one is in the context of matrices, M for a matrix, and this group here is these matrices M. You're given 2 by 2 invertible matrices. Now we've talked about this several times in the past. Invertible means that you can find the inverse of a matrix belonging to this group, and that matrix, its determinant will be non-zero. Right? That's a condition that a matrix can be inverted, so that you can find m to the -1 in a sense. All right? And the entries, the values in the matrix are real numbers. They're with real entries. And you're mapping matrices to non-zero real numbers. Okay? Now that's mapping from group to group, mapping from element to element, more specific. So A here is one of these 2 by 2 invertible matrices. So A is just a matrix, okay? a member of this group. And the determinant of that matrix, now that's just a real number in this case, because we have real entries. We don't have complex numbers in this matrix, so they're only reals. So the determinant must be real. Okay. The determinant of that matrix will be a non-zero real number. All right. Now we've proved earlier. Go back to earlier lectures where we talked about, well, several times we've talked about this. We've proved that this mapping is homomorphic. All right. Using this property. All right. So as above, let's find the kernel. And let's find the image so that we can plug them into here and here in the first isomorphism theorem. Okay, so what is the kernel? Now remember what the kernel is again? It's the subset of your original group G, so it would be a subset of these matrices, right? All of which map to the unit of your target group. So we can ask what is the unit of this target group? Well, talk about the reals, the non-zero reals. The binary operation here is just ordinary multiplication. This binary operator here is matrix multiplication. Right? So these two binary operators are different. This is matrix multiplication. This is just ordinary number multiplication. Okay, so what is the unit of this group? Well, it's just 1. Right? Just the integer, well, which is a real 1. Okay, so you're mapping a matrix that gives you determinant whose value is 1. Right? So your kernel is going to be a set of all, it'll be an infinite set of all those matrices whose determinant equals 1. Make sense? Okay, so let's call that set U for unit. Unit in the sense that for all those matrices, their determinant value is 1. Okay. What about the image? So what values can this f take? You know, well, can be just about anything, right? If you think about it. I mean, because you know, what are the values of f of a? A is just any old 2x2 invertible matrix, right? And the determinant of a matrix is a real number, but this matrix can be anything, right? So you're suspicious that this f, the set of all these f's, different f's, yeah, in other words, the image of it, is just going to be r. Well, it can't be 0, right? We can't have a determinant here being 0. So it's just r star, you know, non-zero reals. For example, here's a matrix. Here's A, where we have just some non-zero real number here, 0.01. Now the determinant of that is just r star, right? And because of the star, it's not 0, right? So the image is all these possible, it's the set of all these possible values. Well, r could be anything except 0, right? Therefore the image is the set of reals, just big R star, okay? So we know what the image is, we know what the kernel is, it's U, so the set of all those matrices whose determinant is 1 equals 1, right? So we just plug in, here's our kernel here, it's just U, and here's our image of f, right, which is r star, so we have our second relation, right? So you're seeing the pattern emerging, right? Just keep doing the same thing. We've done it twice already. Done 4 times by the time finish this. You'll have a pretty good idea how it's done, right? Okay, third example. What are we doing here? We're mapping real numbers into non-zero complex numbers. Binary operation for the first group, big G is you adding. Binary operation for the second group, group H if you like, is just a complex number. It's not just real number, complex number multiplication, because we're talking in the context of complex numbers. Right, so that's mapping group to group. How do you map element to element? More detailed, more specific. Well, you take any real number, x here, from this group G, and you map that into a complex number of this form. So e, exponential, e to the 2 pi I x. Okay. All right. This f, is it homomorphic? We haven't done this before, I think, in terms of proving it homomorphic, so let's just quickly do it. Right? So we're trying to show fxy is equal to fxfy, right? The usual homomorphic form. The binary operation here is plus, right? For your big group G. So f of xy will just, you've got x plus y here, so put x plus y here, which gives you this, right? Now you can split this up. These are just exponents of your e, your exponential e, right? So you can split this up into 2 parts, like this. But e to the 2 pi x from this definition is just f of x, and this is just f of y. Okay, so you've got this equals this, and therefore f is homomorphic, because that's the homomorphic form. All right? Okay, so we know it's homomorphic, so let's ask what's the kernel? What will the kernel be? Now, again, what's the definition of a kernel? It's the subset of G, your starting group, that all of whose members map to the unit of your target group. Well, what is the unit of this target group? In the context of complex numbers,